Hello, and in this video we're going to be looking at kinetic energy. Okay, before we get stuck in, I want to remind you that the formula for kinetic energy is a half mv squared. So we can calculate the kinetic energy of an object by doing half times its mass times its speed or velocity. They work the same way here, squared. Okay, and so there we are. And again, this is responsible for an object's movement, right? It's to do with the speed of an object. So there we are. So you should remember that from chapter 2 when we looked at work, energy and power, or even from GCSE physics. But there we are, and you do need to remember that that's not in the formula book. Okay. So previously we've looked at collisions. So let's say we have two particles, two balls here, 1 and 2. And so they're going to collide into each other. So let's say the first one bashes into the second one and vice versa, like this. Okay. And what we've looked at so far are the speeds, okay, before and after the collision. And we've looked at tools to deal with this. So we've looked at conservation of momentum and restitution, right? And so we know that the speeds change, right, due to the collision. So the speeds change due to the collision. But more specifically, the speeds change because the energy changes between the two particles, right, between the two objects. And more specifically, that's due to the change in kinetic energy, okay? Because so the speeds change because the kinetic energy changes. Okay. And remember, kinetic energy is the energy responsible for the speeds, right? So if the kinetic energy changes, then so does the speed. Okay, so that's the idea. So so the kinetic energy changes before and after the collision. Okay, so we can say that the change in kinetic energy before and after the collision, well, we can say the change is going to be the kinetic energy after. I'm going to say the total kinetic energy after. Take away the total kinetic energy before. Okay. Okay, so that's the change in kinetic energy. Remember, it's very similar to what we looked at in chapter 2. So we looked at kinetic energy there, and so we saw that the change in kinetic energy is the kinetic energy after versus before. Okay, but we can be a bit more specific. Okay, so I've used the word total kinetic energy because obviously we're dealing with two particles here. We can further split these up into the kinetic energy, the Ke after of the two individual particles, right? Okay, so essentially what we can do is to work out the change in the total kinetic energy overall, we can just consider the individual kinetic energies of these two objects we've got here, right? So so we get this formula here, okay? but we can be a bit more specific than just saying change, right? Because yes, we know it changes, but specifically we're going to be losing energy. Okay, kinetic energy will be lost. Okay, that can be for many reasons. For example, it might be transferred to sound. If it makes a large bang sound, there might be a lot of forces going on, so there might be some energy used for that. There's many reasons why we lose kinetic energy in a collision, okay? But we do lose kinetic energy. We can never gain any energy, so we lose it pretty much. So I'm going to say kinetic energy is lost after a collision. So what does that mean here? Well, this change then is going to be a negative answer, okay? It's going to be a negative change in energy because the kinetic energy afterwards is going to be less than the kinetic energy we started off with before. So this is going to be a negative answer, so it's going to be a negative change. So we can then specify that the loss in kinetic energy is going to then be the other way around. So if we kind of make it positive, because the loss, remember, loss in energy, it's just a physical number, right? So we don't care about the negative. Anyway, the actual loss is going to be the total kinetic energy before, take away the total kinetic energy after, okay? And so we're going to be using this sort of formula here, okay? There we are. Now you could make this a lot more mathematical if you consider the speeds and the masses. I'm not going to do that here because I think it's a very long formula, and I think for this, if you just use the concept, I think you can work it out by yourself rather than need an explicit formula for the energy change. So we're just going to be using this, okay? So hopefully with me here. So the loss in energy is the energy we started off with initially, but then we lose some energy afterwards, okay? And so there we are. Okay, so let's have a look at some questions then. So here we're told two spheres P and Q of masses 4 and 2 are travelling towards each other in opposite directions along a straight line on a smooth horizontal surface. And initially P has speed 5 and Q has speed 3. After the collision, the direction of Q is reversed and travelling at speed 2. Find the velocity and the loss. Find the velocity of P and the loss in kinetic energy. Okay, so it's a bit wordy, but what's going on is, if we draw a diagram, we have P and Q. And so P has mass 4 and Q has mass 2. So what about the speeds? Well, we're told they move in opposite directions towards each other. So P is going to go to Q like this, and then Q is going to go the other way to P, okay? And I'm told that P, the speed is 5, and for Q the speed is 3, okay? And so there we are. Then after the collision, well, we're told that after the collision for Q, the direction of Q is reversed, which means if Q was going backwards before, it's now going to go forwards in the opposite way. And I'm told the speed afterwards is 2, okay? And there we are. We're not told anything about where P goes. So again, so what we can assume is that, let's say it just goes forward, right? It's best to assume it goes forward because it makes the calculation a bit easier because it's in the positive direction by default. But it really doesn't matter. You can assume it. We don't know where it goes, forwards or backwards. But I'm just going to take it to go forwards there. So hopefully happy with my setup here. So now we're going to apply my standard formulas. So momentum, okay. So if we look at P, well, before it's speed 5, so it's going to be the mass of 4 times 5. Then for Q, it's going to be mass 2, and then 3 for the speed, but that's in the negative direction, so it's going to be minus 3. And that's going to then equal afterwards, there's going to be 4 lots of V1, add 2 lots of 2. Hopefully happy with that. And so we just simplify, so it's going to be 20 minus 6 is going to be 4V1, add 4. And actually we can solve this for V1 here now. So this simplifies to 14 is 4V1, add 4. Therefore, we just get 4 lots of V1 to be 10, and so therefore V1 is 2.5 if we divide by 4, and that is my answer there. Cool, so hopefully you're happy with that. Now, that's 2.5 then here for V1. And here we are. And my answer is positive, which tells me that I am correct, that it is indeed moving forward, right? So if I got a positive answer, that tells me it's actually moving forward. If I had say minus 2.5, I'd have to flip it. And then it'd be positive, but I don't need to worry about that, okay? And so the velocity of P is that it's moving forwards with speed 2.5. And there we are. Now it wants to ask for the loss of kinetic energy. Okay, so now we're going to look at the loss in kinetic energy. And remember, loss in kinetic energy, which we discussed at the start, is the kinetic energy before the collision. Take away the kinetic energy afterwards. Okay. Now, if we break this down, firstly, the kinetic energy before. What we can do is look at both the particles before the collision. So for P, the speed is 5. So if we do P first and the mass is 4, it's going to be a half times 4 times 5 squared. Because remember, kinetic energy is a half mv squared, right? Make sure you remember that. We looked at that in chapter 2. So that's for P then before. Hopefully happy with that. Then for Q. For Q, the mass is 2 and the before speed is 3. So it's going to be half times 2 times 3 squared, right? So we're going to add that on. And so this is my total kinetic energy before the collision. Hopefully happy with that. So if I just work that out now, put it in the calculator. 59. Then we can similarly work out the kinetic energy after the collision. So firstly for P, after the collision, P has speed 2.5 and the mass of 4. So it's going to be half times 4 times 2.5 squared. And then for Q, well, after the collision, Q has speed 2 with mass 2 as well. So it's going to be half times 2 squared for Q. And again, if we work all that out, put it in the calculator, 16.5 there. And again, this is all in joules, right? This is my kinetic energy in joules. Therefore, we can calculate the total loss in kinetic energy. And that's going to be, again, if we look at our formula, kinetic energy before, take away kinetic energy after. So that's going to be 59, take away 16.5. And so I will get the loss in kinetic energy of 42.5 joules. And that's my total loss in kinetic energy there. Okay, then we've got this question here. Okay, so again, if we draw a diagram. Okay, so this is just what we looked at the start of the chapter. So again, we got two spheres A and B. The mass of A is 3 and the mass of B is 5. Now, I'm told these two move towards each other in opposite directions. So again, A's going to go to B like this, and B's going to go to A like that, in the opposite direction. So there we are. And their speeds are 3 and 2. Okay, so there we are. And so we also told that E, my coefficient of restitution, is 3/5. Okay, and that's all we're told. So it says to find the velocities after the collision. Now, so let's say firstly for B, it's going to move here. Let's say I'm going to call that V2. And then A is going to go the other way, V1. Okay, generally, as a good rule of thumb, you want to assume for the second particle is going to move to the right. Because pretty much never it's going to move to the left. But there we are. Anyway, with that in mind, we can first apply momentum. So again, let's take forwards as positive. So that's going to be the total momentum. So 3 times 3 for A, because that's the before speed for A. Then 5 times 2 for negative 2 for B, because the speed 2 is going to the left in the negative direction. Okay, so then that's going to equal 3 lots of minus V1. Again, that's negative. Add 5 lots of V2. Okay, so hopefully happy with that. So we can simplify this to get 9 minus 10 is minus 3v1 add 5v2. Therefore, we get minus 3v1 add 5v2 equal to minus 1. And that's my first equation. Then I can also use restitution. And so remember, the formula I like to use, it's a very nice, safe formula. Is V2 minus V1 over U1 minus U2. Again, we've used that in the first part of the chapter. So in this case, E is going to be, well, V2 is V2, right? And then minus V1, but V1's negative, so it's going to be minus V1, okay? Then U1, so the speed before, that's going to be the speed of the first particle A, which is 3. Take away U2, which is going to be this one. And now that speed is 2, but again it's negative, so it's going to be minus 2. Okay. Okay. So there we are. So that simplifies to V2 plus V1 over 3 plus 2. Now we also know that E is 3/5, so we can say 3/5 is going to equal V2 plus V1 over 5. Okay, so if we cross multiply, we times 3/5 by 5. No, what we could say 15 is 5 lots of V2 plus V1 if I break it down. So then I can just expand that to get 5V1 add 5V2 is 15. Or you could just simplify, divide by 5 to say V1 add V2 is 3. Okay, so there we are. Okay, and there we are. Hopefully happy with that. So we've got these two equations then. Okay, so if I bring the first one down here, I have minus 3V1 add 5V2 is minus 1. And then I also have V1 and V2 is 3. So I have simultaneous equations here. I need to solve them. So if I triple the second equation, so 3V1 and 3V2 is 9, then I bring down the first one again. Hopefully what you can see we can do is now add them to get rid of the V1. Okay, because that will, because the V1s will cancel because they're opposite. One's positive, one's negative. So that'll go to 8V2 is 9 minus 1, which is 8. So therefore V2 is very nicely just 1. Okay. Then I can find V1 by substituting V2 in. So sub V2 into, let's say, the second equation here. Let's just say V1 add V2 is 3. So that means V1 add 1 is 3. Therefore V1 is going to be 2. Okay. And there we are. So I can add that on then. Okay. And so there we are. So V2 is 1 and V1 is 2. Okay, and they're all positive, which means indeed my directions were indeed correct. They are actually travelling backwards and forwards here. Okay, there we are. Then in part B it says find the loss in kinetic energy. Okay, so now we need to find the kinetic energy loss. So what we're going to do then, again, loss in kinetic energy is going to be the kinetic energy before. Because again, we're going to expect more energy before than afterwards. So if you work that out, again, work out the kinetic energies individually. So firstly, for the first part, for the first ball A, the mass of the speed is 3. The mass is 3 as well. So it's going to be half times 3 times 3 squared. and then we're going to add on the kinetic energy of B. So B, so for B, the speed is 2 initially. So half times 5 times 2 squared. Then we're going to take away the kinetic energy after. So that's going to be half. And then for A, the speed back afterwards is 2. So it's a half times 3 times 2 squared. Add the final kinetic energy for B. So the speed afterwards is 1. So it's a half times 5 times 1 squared. And there we are. Okay. And so just chuck all that in the calculator. We get 15. Okay, we get 15 joules, and that is my loss in energy there. Okay, then we got this question here, which is interesting. So let's have a look. So we told a particle mass 3 is moving with speed 6, and it collides directly with a particle mass 5 moving in the opposite direction with speed 2. The particles coalesce and move with velocity v after the collision. Find the loss in kinetic energy due to the impact. Okay, what makes the question interesting? Hopefully picked up on this word coalesce here. Now we very briefly looked at what that means. We've not actually, I've not looked at an example like this yet. So let's have a look how we deal with this. So coalesce is a fancy word for saying stick together. Or combined, okay? So essentially the particles then join as one, okay? So if we draw a diagram here, what it's going to look like, so let's say before, we've got these two particles, 1 and 2. The first one has mass 3 and the second one has mass 5. Then I'm told they are moving in the opposite direction. So again, that has to mean they're going to move towards each other like this. Okay, so the first one has speed 6 and the second one has speed 2. Hopefully happy with that. So this is before. Okay, this is before. Now, afterwards, as I said, they join together as one. So what that's going to look like is afterwards, they're going to join as one big particle with the combined mass because they're joined together as one. So if the individual masses are 3 and 5, they will combine to 8 kilograms there. Okay. And so not only that, because they just join as one now, they're going to have a sort of common speed, right? And so they're going to have the same speed v. Okay. And there we are. Okay. So we need to find v. Okay. Now, we're going to do our usual method then. So firstly, let's actually do restitution. Now, what you need to know is in this particular unique case of coalesce, so when things join together like this, you also need to know that E is specifically 0 here. Okay, and actually we can see why E has to be 0 here. Okay, because let's say let me use the first diagram, right? Let's use this diagram here. If they're sticking together, they're going to move in the same direction forwards, and they're going to have the same speed v. Okay, like this. Okay, and so there we are. So we can also say this, right? And so if it was to then calculate E in the usual way, so v2 take away v1 over u1 take away u2, well, in that case this is v2, right, v, but this is also v1, so I'm going to take away v, and then you can see we're going to get 0, right? But let me just complete this. So u1 then is going to be 6, take away the -2 because it's going in the negative direction. You can see that E will then be 0 because effectively the speed of separation goes to 0, okay, because they're not separating. they're not separating, they're stuck together, right? So you can see, therefore, E is 0 here, in the case they stick together. Okay, but there we go. So you need to remember E is 0. So we can't use E here, okay? So the only thing we can use, if I get rid of this diagram here, is momentum, okay, to work out V. So, okay, so if I use momentum here, it's going to be 3 times 6, and then 5 times, again, minus 2 here, because it's a negative direction. Again, forwards is positive. So minus 2 is going to equal then 3 times V, and then 5 times another V. And then you can see we can solve for V here. And so this simplifies to 18 minus 10 is 3V add 5V. Therefore, we just get 8V to be 8. And quite nicely, we can then deduce that V is just 1. And there we are. That is my my speed of both of them afterwards. So they're both moving at speed 1. Okay. And hopefully you're happy with that. Then it wants to find the loss in kinetic energy. So again, my standard formula here, the loss in kinetic energy is going to be the kinetic energy before, take away the kinetic energy afterwards. So firstly, the kinetic energy before. So before the collision, obviously we got the first particle with speed 6 and the second one with speed 2. So it's going to be half times the mass. The first one, the mass is 3, then lots of 6 squared, and then a half, and then for the second particle, the mass is 5. So it's going to be 5 times 2 squared. And so if we put that in the calculator, we get 64. Okay, and that is my kinetic energy before. Then the kinetic energy afterwards. Okay, well, afterwards they both have this speed 1, which we just worked out, right? So it's going to be, for the first one, it's going to be half times 3 times 1 squared. And for the second one, it's going to be half. For the second one, it's going to be half times 5 for the mass, and then 1 squared as well. And so if we work all that out, we get 4. Okay, and there we are. 4 joules there. Therefore, we can say that the loss in kinetic energy is going to be before, which is 64, take away afterwards, which is 4. So we get 60 joules. So we lose 60 joules of kinetic energy there. Okay, now we're going to be looking at some questions where it's sort of set in like a real life scenario. Now, these questions are a bit weird. I don't know, the textbook for this part seems to just be full of these type of questions, but in the exam, I've not really seen questions like this. So there's a huge disconnect between the textbook and what they seem to ask in exams in this sort of scenario. So I'm not going to spend too long on these questions, but I will go over what the textbook does just to, I guess, help with that. But yeah, let's have a look at this then. So here we're told a gun of mass 600 kilograms fires a shell of mass 12 horizontally with speed 200 meters per second. Firstly, find the velocity of the gun after the shell's been fired. Okay. So what's going on? Obviously, you can see here we've got some sort of cannon, some gun, and then we've got the bullet, which we call a shell, here. Okay, so it fires and the shell leaves the gun. Okay. So what we're going to consider is before the shooting or firing. Okay, before the firing and after the firing. So before the firing, again, I'm going to draw the same sort of diagram, 2 little circles. Again, obviously not accurate at all to what the gun or the bullet looks like, but these are my so-called particles. So I'm going to call this my gun, and then this is my bullet. So before the firing, I'm going to move it up here. Before the firing, well, they're not firing yet, okay? Obviously, they've not fired, right, because it's before the firing. So actually, both the gun and the shell, the bullet, can't be moving because nothing's done, nothing's happening yet. Okay, so it's standing. They're both standing still effectively. So they both start at rest with 0 speed. Okay, so there's no motion before the firing. Okay, then of course it fires, and then afterwards we have this. Okay. So what happens after the firing? Obviously now there is motion. So obviously you can see here the bullet is definitely moving forward. We can see that right in the diagram. Okay, I'm going to call that V2. Okay, like usual. But what about the gun? Now, let's say we don't know what happens to the gun. So we don't know if it's going to move forwards or backwards. You might presume it moves forward. Okay, might be a fair thing to think. Okay, so I'm going to call that V1. Okay, again, so there we are. So I'm just going to those are my speeds. Okay. Oh, we actually know the shell has speed 200 after it's fired, so we can add. We know what V2 is. It's 200. Okay. So we just need to find V1 here, the speed of the gun. Okay. Right, hopefully with me here. Lastly, I can just add my masses. So the gun has mass 600 and the bullet has mass 12. Okay, and so that's my diagram now. Hopefully happy with that. So the idea is before the firing, nothing's moving, and then afterwards it's moved, and so there we are. Okay, so it's a bit unusual, but there we are. Now, again, we can now that we've got our diagram, we can now apply our usual techniques. So we've got momentum firstly. So it's going to be 600 times 0 and then 12 times 0. Then afterwards, it's going to be 600 lots of V1, add 12 lots of 200. Okay. And so we simplify this, we get 600 V1 plus 2400 equals 0. Okay, therefore V1 is going to be minus 2400 over 600. So if we simplify that, we get V1 to be 4. Okay, so minus 4. Okay, and so it's a negative, which implies, well, it tells me, so if this is so if this V1 here is minus 4, then of course it has to actually be moving in the opposite direction, and then it'd be positive 4. Okay, so it tells me when this cannon gun thing shoots the bullet forward, it goes backwards. That's called recoiling. Okay, so if you're slightly familiar with the guns, a gun will recoil backwards to allow the bullet to shoot forward with quite some speed. Okay, so there we are. Okay, then in part B it says find the total kinetic energy generated on firing. Okay, so this is an interesting scenario because we start with 0 speed and then we end up gaining speed. Okay, so it's quite interesting because then that tells me I'm gaining kinetic energy instead of losing it. Okay, now I've had to look this up. I'm not that familiar with guns. The idea is there's something called gunpowder, which sparks a chemical reaction. That reaction gives basically then supplies kinetic energy. So sort of chemical energy is transferred to kinetic energy, which allows the gun to fire the bullet. Okay, so in this case there's sort of an external force, an external energy being supplied, which allows it to move forward. Okay, so that's why in this case it's a gain in energy. You might see that in movies or shows. So you might see that the guns, when they fire, they have like a huge smoke. Okay, there's smoke off a gun when it fires. That's because of the reaction, the gunpowder burning. Okay, which but then that gives off kinetic energy to allow the bullet to shoot. Okay, So there we are. Anyway, moving on from that, so we can calculate the kinetic energy gained in this case. Okay, so that's going to be, well, so that's going to be the kinetic energy after take away the kinetic energy before. So the kinetic energy afterwards in this case, that's going to be, the mass is 600 for the gun, the speed is 4, so it's going to be half times 600 times 4 squared, and then a half times, and then the mass of the bullet is 12, and the speed is 200, so it's 12 times 200 squared, and then the kinetic energy before. Now, both the speeds, the gun and the bullet, both of them are 0 before, so clearly there's no energy there, okay? So we don't need to bother working that out, it just goes to 0, okay? So therefore we can see that the kinetic energy gained here, 244,800 joules, okay? So quite a lot there, okay? And so there we are. That's how much kinetic energy is gained overall there, okay? But usually, pretty much every question, that's not going to be the case, because there's no external force or external thing that's going to supply energy. Usually when we look at collisions, we're just focusing on the two objects themselves. There's no external factor that's going to mess or affect the energy. So usually we should expect loss in energy when there's no external thing acting on the two objects. But in this case there is. Okay, there's some gunpowder in the gun that supplies extra energy. So there we are. Okay, part C says show that the ratio of the energy of the gun to the energy of the shell is equal to the ratio of the speed of the gun to the speed of the shell. So it's essentially saying find the ratio of energy to speed, okay? Pretty much, okay? So firstly, let's consider the energy, okay? So let's consider the energy of the gun and the shell separately. So firstly, I'm going to consider energy. So the ratio of the two energies. So, so the energy of the gun, let's work it out step by step. So that's going to be half times, now the mass of the gun was 600 and the speed was 4. And that'd be squared. If we work out the energy of just the gun there, the kinetic energy, that's going to be 4,800. Likewise, the energy of the bullet, okay, well, it's going to be half times the mass, which was 12, I believe, and the speed was 200, I believe. Let me check. Yes, so if I work all that out, I get 240,000 joules. Okay, so there we are. And that makes sense with my answer, because the overall gain in kinetic energy are these two numbers added together. Okay, so indeed my answer should be right. Anyway, so therefore the ratio of the energies, so it's the energy of the gun to the shell, that's going to be 4,800 to 2,400 joules. And so we can simplify this. So gun to the shell. So we can simplify this. So this is my rate, my energy of the gun to the bullet. Simplify this ratio down, and actually it divides quite nicely. We can just divide by the whole 4,800, and we get 1 to 50. Okay, quite nicely there. So there we are. Then we're going to look at this speed, because now it wants me to consider the speeds of the two of them. But that's quite nice. Well, we don't need to work anything out because we know what the speeds are. So the speed of the gun to the bullet is 4 to 200, right? And then that simplifies to 1 to 50. And so therefore, these two ratios are equal. Okay, and so there we are. So therefore the ratios of energy and speed are equal. Okay, now that's quite significant because we discussed that usually the objects in a collision lose speed because they lose kinetic energy, and so they have to be linked. So we can see that the ratio of the speed to the energy gained or lost has to be the same. Okay, so there we are. Okay, then we've got this example here. So we've got another sort of scenario based question. What on earth is going on here? What's ultimately happening here is we have two particles, or two balls if you will, essentially at either end of some string. Okay, that's ultimately what's going on here. So this is A and B connected to some string. Okay, now what's happening is originally they're both at rest, so the string is a bit loose. Okay, it's slack. Okay, it's a bit loose, it's not being really stretched or stressed in any way, so it's going to be a bit loopy like that. Okay, so it's quite a loose piece of string. Okay, it's not being stretched at all. Hopefully you can see that. So they originally both start at rest, but then A is then projected with speed 6, and it's going to go away from B, so it's going to then there's going to be some speed applied to it of 6, and it's going to be pushed to the left. Okay, so what that's going to happen then is the string is going to then be stretched to the left. Okay, and so eventually we get this situation where the string is now sort of tight. Okay, it's going to be tight, it's not going to be it's going to be quite rigid, stretched if you will. Then we have A and B then, and now the string is it's not loopy, it's not slack at all, it's not loose, it's now completely rigid. Okay, and so you can imagine then as A would then push forward, it would push B along with it. It will tag along B. Okay, P will be pushed along as well. Okay, and so and then they move with the same speed afterwards. Okay, in the direction of A. So it's gonna have the same speed V. Okay. And so there we are. And so if I again recall, B is originally at rest, so 0 speed here. So this is before and after. Okay, so hopefully happy with that. Again, it's a very unusual scenario, but that's what's happening. Okay, and so hopefully happy with that. So actually I can just simplify this to my usual diagram then. So if I call this A and B, so before the motion, okay, A is moving 6 to the left and B's at rest, and then afterwards they move to the left, both of them with speed V. Okay, and hopefully happy with that. So there we are. So I'm just copying what I've done up here into this diagram here. So I'm just copying all the speeds out before and after. Also the masses are 200 and 300. Now it's in grams, which is an issue. It has to be in kilograms. Okay, so that's going to be 0.2 kg and 0.3 kg. Okay, because remember again, 1 kilogram is 1,000 grams, so we need to divide by 1,000 to get it in kilograms. Okay, so actually the mass we're going to use is 0.2 and 0.3. Okay, so there we are. So now we can apply our normal methods. Okay, now we can apply our usual techniques. So if we use momentum, again, forwards is positive. So that's going to be 0.2 and then minus 6 because it's negative direction, and then 0.3 lots of 0. It's going to equal 0.2 lots of minus V, and then 0.3 lots of minus V as well. Okay, so there we are. So that's going to get me, if I simplify it, minus 1.2 is going to equal minus 0.2V minus 0.3V. Therefore, I could say 0.5V will go to 1.2. Okay, therefore V is going to be 2.4 if I divide by 0.5, and that is my speed afterwards. Okay, and so that is the speed of both of them after the string becomes taut. Okay, so that's when the string effectively becomes sort of stretched. Okay, I'm not going to go into the specifics of strings here. You're going to have to wait until year 2 when you look at the strings chapter. But yeah, for now, there we are. That's my speed. Okay, then in part B, then it wants the loss in kinetic energy. Okay, so again, now we're going to do the normal thing. So that's going to be the loss in kinetic energy. It's going to be the kinetic energy after. Kinetic energy before, take away kinetic energy after. Again, if you was to do it the other way around, it wouldn't be a huge deal because you should just get a negative answer. So then you'd have to make it positive to get the loss. Anyway, so the kinetic energy before. So before the collision, obviously we can see for A it's 6. So it's going to be half times 0.2 times 6 squared. But then B is going to be 0, right? Because it starts at rest. There's no speed initially, right? So it's 0 there. So it goes to 0, then take away a half of 0.2, and then for A, well, it's V, right? It's 2.4, right? So 2.4 squared, and then for B, it's a half times 0.3, lots of 2.4 squared. So if we put all that in the calculator, that gets me 2.16 joules, and that is my loss in energy there. Okay, now we're going to be looking at harder problems where there's algebra and even impulse thrown into the mix here. Okay, so we're going to be looking at some exam questions at the end of this, but the idea is there's algebra. It looks scary, but the processes, the formulas we use are going to be exactly the same. Okay, so again, if I draw a diagram, so I've got A and B. So A has mass m and B has mass 3m. And, okay. And I'm told A has speed u and it's going to collide into B. So u here, okay? That's my speed u. And B is at rest. I'm told B is at rest, okay? So B has speed 0 here, okay? And those are my before speeds. Afterwards, well, I'm not told anything else. So let's say both A and B move forward, right? I think that might be plausible. Okay. Obviously B's gonna have to move forwards, right? If A's gonna push into B and B's not moving, it's gonna have to move forward. So that's going to be V. I'm going to call that V2, and then let's say V1 here. Okay. So those are my speeds. Okay. So again, firstly, I'm going to apply momentum. So for A, the mass is m times the velocity, which is u. Okay, so m lots of u. Then for B, it's going to be 3m for the mass, but the before speed is 0. So that will go to 0. That's going to equal m, and then the afterwards, the speed v1, and then 3m lots of v2. Okay, and there we are. So we can simplify this. So we're going to get mu equals mv1, add 3mv2. But of course, we can divide by the m, cancel all the m's out. So then we can say v1 add 3v2 equals u. Okay, and that's my first equation. Okay, then we can apply restitution. So remember, that's saying E is v2 take away v1 over u1 take away u2. So in that case, well, we have v2 and v1 here. So simply v2 take away v1 here. and then u1, so it's the speed of the first particle A, that's going to be u, and B has speed 0 initially, right? So it's u take away 0. So that simplifies to v2 minus v1 over u, okay? And so we can cross multiply to get E lots of u equals v2 take away v1. And there we are, okay? That's my second equation there. Again, there's a lot of algebra here, but yeah, okay. So now if I combine them, if I rewrite them here, if I state them again, so we have v1 add 3v2 is u, and also minus v1 add v2 is eu. So I've got these simultaneous equations here. Again, there's a lot of algebra, a lot of letters here, but if you just pause, have a think, we can simply add these equations together to get rid of v1. Okay, so the idea is to still solve for v1, v2. We can add to get rid of v1. So then we're going to get 4v2 is u plus eu. Okay, hopefully happy with that. Then I can just divide to say v2 is then just a quarter lots of u plus eu. And actually we can factor a u out. Okay, so lastly we can say v2 is u over 4 lots of 1 plus e. And that matches the expression they've got here. Okay, effectively. So there's my answer. That's the speed of B. Then the speed of A then, okay. So we know what v2 is. I'm going to sub v2 into one of the equations. So let's substitute it into, let's say this one here. Minus v1 add v2 equals eu. Okay. Therefore, we can say minus v1 add v2, which is u over 4 lots of e plus 1. That's going to equal eu. If I expand this, I'm going to get a quarter EU plus a quarter U equals EU. Hopefully happy with that expansion. Okay, again, make sure you don't trip up on the algebra. So there we are. Then I can move everything to one side. So just minus V1 is going to be EU, take away a quarter EU, take away a quarter U. Then what do you notice? I have common terms EU. I can collect them like terms. So 1 EU take away a quarter EU is 3/4 EU minus a quarter U. Okay. And so lastly, I can just flip the negative. So V1 is a quarter U minus 3/4 EU. And I can also factor a quarter U out. Okay, factor a common factor. So that would be a quarter U of 1 minus 3E. And that is my expression for V1. Okay, hopefully you're happy with that. Okay, make sure you go step by step and you're comfortable with all the algebra here. Okay. Okay, there we are. Then it says immediately after the collision, the total kinetic energy is a 6 mu. Now, that's not telling me the loss in kinetic energy. That's telling me the kinetic energy after the collision. Okay, so I'm gonna explicitly state that here. Ke afterwards is what is it? This is 6 mu squared. Okay, so make sure you read the question clearly. It's referring to the speed afterwards, not the loss in energy. Okay, different things. So then if we were to calculate the kinetic energy afterwards, well, it's going to be half. So it's going to be half times the mass of the first particle, which is m, and then times by V1 squared. Okay, so it's m lots of V1 squared, then it's going to be half times the mass of the second one, which is 3m times the final speed V2 squared. Okay, hopefully happy with that. Again, try not to be put off by the algebra, but there we are. Okay, but then we can substitute, actually no, let me simplify. So it's going to be half m lots of V1 squared at a 3 over 2m lots of V2 squared. And now we can substitute my two expressions in. Okay, so it's a half m. Now V1 was a quarter u times 1 minus 3e. and that would be all squared. Again, pay attention to your brackets. And then 3 over 2m, and then v2 is here is a quarter u of 1 plus e. So it's going to be a quarter u of 1 plus e, all squared there. Okay, so then we can just simplify. So it's going to be a half m times. So if we're squaring this all out, we're multiplying it again. So firstly, we're going to do a quarter u times itself. So it's going to be 1 over 16u squared of 1 minus 3e squared. Okay, and then 3 over 2m, and then again a 16th u squared of e plus 1 squared. Okay, and so if we tidy this up, we're going to get 1 over 32 mu squared, lots of 1 minus 3e squared. If it and then 3 over 32 mu squared, lots of e plus 1 squared. Okay, hopefully happy with me with this up to here. So again, make sure you're happy with the bracket expansions here. So now I'm going to multiply these. Well, actually, no, before we do that, let's have a look. So again, this all has to equal a 6 mu squared. Okay, so now I'm going to equate this. I'm going to equate all of this to this as 6 mu squared. Okay, because these expressions are the same thing. They both are the kinetic energy afterwards. Okay, but what do you notice? Well, actually, I can factor out 1 over 32 lots of mu squared here. Okay, of both terms here. So that's going to be 1 minus 3e squared, add 3 lots of e plus 1 squared. Again, hopefully happy with that factorization I've done here. Okay, that's going to equal 6 mu squared. Then I can divide by mu squared. I can cancel these terms out. So therefore I get 1 over 32 lots of 1 minus 3e squared, add 3 lots of e plus 1 squared is going to equal a 6. Okay, and hopefully this point is a lot more comfortable because you can see we're just going to have to solve a quadratic. Okay. But firstly, let me multiply by 32 to both sides to get rid of the fractions. So I have 1 minus 3e squared, add 3 lots of e plus 1 squared, is going to equal 32 times a 6, 32 over 6, right? Hopefully happy with that. So multiply both sides by 32, and so 32 over 6 simplifies to 16 over 3, okay? But there we are. So now it's become very apparent, hopefully, that we're going to get a quadratic in E to solve. Anyway, so now we're going to need to expand the brackets now. I'd probably do this somewhere separate. Let me do it here. So firstly, 1 minus 3e squared, 1 minus 3e, 1 minus 3e. If I expand it, so if I expand this, I get 1 minus 3e minus 3e is minus 6e. And then plus 9e squared. So I'm going to sub that in. And then if I expand e plus 1 squared, that's going to be e squared plus 2e plus 1. Okay. Again, if you're not a bit shaky, do that expansion step by step. But hopefully you get to that. And that's going to equal 16 over 3. And then we can just clean this up. So we're going to get 1 minus 6e plus 9e squared, add 3e squared, add 6e plus 3. And then I'm going to subtract this to the other side, and that's going to equal 0. And so then eventually we're going to get 12e squared, and then the e's cancel, minus 6e plus 6e cancel. So then we're going to get 1 plus 3 minus 16 over 3. So 1 plus 3 minus 16 over 3 gets me minus 4 over 3. And that's going to equal 0. So hopefully happy with that. Now, this is quite nice to solve. So now, if I proceed, Let me get rid of this now. Let me get rid of this. Okay. So now I can just solve for E. So I'm going to get 12E squared is 4 over 3. Then E squared is going to be 4 divided by 36, right? If I divide by 12. So therefore E is going to be the root of 4 over 36, which simplifies to 2 over 6. Okay, remember we don't do plus or minus because E cannot be negative. Remember E is between 0 and 1. Anyway, so there we are. So it'd be 2 over 6, which simplifies to a third. And that is my value for E. There. Okay, a lot of algebra there. Okay, again, they love to throw algebra at you. But the process, hopefully you've seen, the momentum, the restitution and all that is the same. Okay, but the algebra there at the end, you're going to have to work through that. But there we are. And there we are. And then for part D, it says, hence show that A is at rest after the collision. So that is referring to, it's at rest after the collision. It's referring to the speed V1 here. So we're going to need to investigate that. Now, we just worked out what E is. So we might be able to try that out with V1. So remember V1 was this expression here. A quarter U lots of 1 minus 3E, was it? Yes. Well, if we sub in it, our newfound value for E, if E is a third, so E is a third, that means that V1 is going to be a quarter U lots of 1 minus 3 lots of a third. And so and then we've worked that out. That's going to be 1 take away 1, which will go to 0. And so the whole thing goes to 0. And there we are. Therefore, it's at rest. This is at rest because the speed is 0. And that's what it means. So there we are. Cool. What an interesting question that is. But hopefully, once you go through step by step, that makes sense. Okay. So then we're told, now we're told this. Firstly, we need to get this quadratic here. Okay. So obviously, I have no idea how we're going to get to that. So we're just going to do our normal procedure and hopefully end up with that equation. Okay. So again, if I first draw my diagram out, I have A and B. Again, the same steps. So A has mass 2, B has mass 3. So A is moving with speed 4, so it's going to move here with speed 4. Then B, I'm told it moves in the same direction, so it's also going to move to the right, but with speed 1. Okay, hopefully happy with that. So then the speed, then I'm told they continue to move in the same direction afterwards. And so for A, the speed is U, and for B, the speed is V here. Okay, and so there we are. Okay. Hopefully happy with that. So then if I now apply my usual techniques, so I've got momentum firstly. So that's going to be for A, 2 for the mass times 4 for the speed, and then 3 for B, but then what? Then 1 here. That's going to equal 2 lots of U and then 3 lots of V. Okay. So that's going to simplify to 8 plus 3 is 2U plus 3V. Therefore, 2U plus 3V will go to 11. And that's my first equation there. Okay, now I could apply restitution. But what I am also told in this particular question, I'm told information about the loss in kinetic energy. I'm told that the loss in kinetic energy is 3. Okay, so what I could also do in this scenario is consider the loss in kinetic energy. And remember, the formula for this is kinetic energy before take away kinetic energy after. Okay, so that's going to be kinetic energy before. So for A, the initial speed is 4, so it's going to be half times 2 for the mass, 4 squared. And then for the second particle, the speed is 1 and the mass is 3. So it's going to be half times 3, lots of 1 squared. Then I'm going to take away from the kinetic energy after. So it's going to be half times 2 times the speed after, which is u for A. So u squared. Add a half, lots of 3, lots of v squared for B. Okay, for the second particle there. And so I can simplify this. So if I work out this first part here, that will go to that will go to 17.5. Okay, so we're gonna get 17.5. Take away that. Now we can simplify this part bit by bit. So firstly, half times 2 is 1, so it's just going to be u squared. And then a half times 3 is 3 over 2. So we're going to get 3 over 2 v squared, okay? So there we are. We can expand this bracket out to get 17.5. Take away u squared, take away 3 over 2 v squared, okay? Now, we also know that the loss in energy is 3. So actually, we can equate this to 3. So that means 17.5 minus u squared minus 3 over 2 v squared is equal to 3. Okay. And so if we kind of move the u and v to one side, we're going to get u squared at 3 over 2 v squared is going to equal 17.5 take away 3. Hopefully happy with that. Hopefully happy up to here. Hopefully happy with all the algebra I've done here. And so that simplifies to 14.5. Okay, and that is my equation. I can't do anything more to that. Okay, you can try and be clever and kind of factorize some way, but it's not worth it. Okay, so we also have this equation here. So actually, if I copy it down here, I know 11. Okay, so if I copy these to equate the other equation for momentum, if you stare at it, hopefully you can see we have quadratic simultaneous equations, which you should be able to solve from GCSE really. But there we are. So don't need to do anything fancy. You don't need to panic, because we can just solve these quadratic simultaneous equations in the way we usually do. Okay. So what we can do is, let's say we can rearrange the second equation. So 2u plus 3v is equal to 11. So this is equation 1 and 2. Therefore, we could say 2u is 11 minus 3v. So u is going to be a half of 11 minus 3v. And so multiplying that out gets me 11 over 2 minus 3 over 2v. Okay, and so there we are. So all I've done there was rearrange this equation for u. Okay, so hopefully happy with that. Okay, then I can substitute that into the second equation. No, the first equation, sorry. So the equation with the quadratic terms here. So that would mean u squared, which is this 11 over 2 minus 3 over 2 v squared, all squared, add 3 over 2 v squared. That's going to equal 14.5. Okay, so hopefully you can see there's going to be a quadratic emerging for v, which might hopefully resemble the equation they want. Okay, so now I just need to expand all of this. So it's an algebra grind here. Now I recommend expanding this bracket separately somewhere, let's say here. So if I expand that, okay, so firstly 11 over 2 times 11 over 2 is going to be 121 over 4, and then 11 over 2 times minus 3 over 2v. If I work that out, that's going to be minus 33 over 4v minus another 33 over 4v. and then add 9/4v squared. Okay, hopefully happy with that. Again, you can convert it to decimals if you want to, if that helps, if the fraction looks too ugly. Actually, I'm going to write actually I'm going to probably I'm going to convert it to a decimal now, actually. So 121/4 is 30.25, then minus 33/4, but then we have another minus 33/4. That's minus 33/2 v. Now that is going to be that's going to be minus 16.5 v. Okay, so that's my v terms, and then 9/4, which is 2.25 v squared. Okay, so now we can sub that expansion into my equation here. So therefore, that will be 30.25 minus 16.5 v, add 2.25 v squared. Then we're going to add on this extra 3/2v squared, so that's 1.5 v squared is going to equal 14.5. And now we can sort of now simplify this. So firstly, 2.25 v squared and 1.5 v squared, that's going to go to 3.75 v squared. Then we have minus 16.5 v, and then we're going to have 30.25, and then we're going to move the 14.5 here to equal 0. And so this will simplify to so 30.25 take away 14.5 will go to 15.75. Okay, and that will all equal 0. And so we get a quadratic. Okay, we get a quadratic for v. Now, what equation do they want? They want me to show that 5v squared minus 22v at 21 equals 0. So we need to somehow sort of change this from 3.75v squared to 5v squared. Okay, so let me get rid of all this business here. So I want to scale the equation, the quadratic. I want to get to 5v squared. So to get from 3.75v squared to 5v squared, what am I going to multiply by? Well, 5. If we flip it and say 5 divided by 3.75, that's a multiple of 4/3. Okay. So now let's multiply 4/3 to every term, and hopefully we get a nice equation that they are after. So then if I do minus 16.5 times 4/3, I get minus 22v, and then 15.75 times 4/3, I get 21. And that, I believe, is the equation they were after. Okay, hopefully happy with that final simplification. So I needed to scale and simplify the quadratic. I needed to scale the equation by this multiplier here. I worked that out by saying if I want to multiply by something, I can do the reverse. So 5 divided by 3.75 has to be 4/3. So that's what I'm multiplying by. Hopefully happy with that. Okay, and indeed, that was the equation they were after. Right, hopefully happy with that. Then it says in part B, hence find u and v. Well, we can find v straight away because now we can solve this equation, right, for v. So we solve 5v squared minus 22v at 21 equals 0. So I can solve that however you want. So we solve this quadratic. Okay, and if we solve that, we get v is 3, or v is 1.4. Okay, now they're both plausible answers, really. Nothing out of the ordinary. They're both positive, they're both nice looking. So which one do we accept? Well, we can't tell just yet. Let's have a look at u. Okay, let's solve for u now. So remember, u was this expression here. So now u is going to be, what was it, 11 over 3. No, 11 over 2 minus 3 over 2v. Sorry, okay? Therefore, let's sub in our two values of v separately. So firstly, if v is 3, the corresponding u value is going to be 11 over 2 take away 3 over 2 lots of 3. Put that in the calculator. We're going to get 1. Okay. Then if v is 1.4, u would then be 3.4. okay. So again, nothing seems out of the ordinary. So we get these pair of solutions. So ultimately, if u is 1, v is 3, or if u is 3.4, v is 1.4. Okay. So these are my solutions to the simultaneous equations. So we need to rule one of these out. Okay. Okay, so I've copied the diagram out for ease here. Again, so my two solutions here look normal, really. Look like normal values, right? Now you can kind of rule out the solution in two ways, okay? You could either think about it, okay? So let's have a think. So if I just play around and plug in the two values, let's say firstly u is 1, then v is 3. Well, that's saying A is then moving slower than B. Okay, so B is going to move further away from A. Okay, B is going to move move faster ahead. Okay, that seems fair, right? We would expect B to then move away from A, right? But if then U is 3.4 and V is 1.4, well now, so now A is faster than B, so they're not going to separate, right? A's still going to bang into B. They're not going to separate because B can't get any distance away from A because A's moving faster still. The core idea is that there has to be a separation after the collision. There has to be a separation, okay, or else you're going to get some weird physicsy thing, right? A's just going to continuously keep bouncing into B, okay, and that's not how collisions really work. They need to separate, okay? So B has to have a greater final speed, okay? Now, if you're not convinced by that, you can do it in a mathematical approach. Let's consider E. We could also rule out the solutions more rigorously, more properly, by just considering E. Again, if I took these values here, okay, so if I said if U is 3.4 and V is 1.4, you can also see that this couldn't possibly be true, because if I calculate E here, well, again, E is V2 minus V1 over U1 take away U2. Well, V2 is going to be 1.4 take away V1, which is 3.4, and hopefully you can see the issue here, okay? Again, U1 is 4, U2 is 1, so it's 4 minus 1. If I work that out, hopefully you can see the issue here is, if I calculate the restitution here, it's going to be minus 2/3. That's an issue. It's a negative, okay? So I'm going to say, but E has to be positive, okay? So E cannot be equal to minus 2/3. So therefore, these values cannot happen, okay? So therefore, U cannot be 3/3. So therefore, U equals 3/3 and V equals 1.4 is not a valid solution, okay? And so you can reason it like that as well. Okay, if you're not convinced about the more sort of physicsy the idea behind this, you can just calculate the restitution and see that also cannot work because it's negative here. Okay, and so therefore the only solution is u is 3, u is 1 and v is 3. Okay, and that is my only solution there. And you could calculate E in this case, and you'd see E would be positive. So E, if this is V2, take away V1, which is 1, but that's now positive. It's going to be positive 2. Okay, so that would be fine. Okay, so there we are. Okay, you would get E to be 2/3 in this case. Instead of negative 2/3, you'll get positive 2/3. So that's great. So this is a valid solution. So there we are. Okay, so hopefully that made sense. Yeah, it's a bit weird, especially towards the end, that justification bit, but hopefully happy with that. Again, kind of visualizing your mind why B has to be faster than A in order to gain distance, to be separation, to separate, and also the restitution here. Okay, now we're going to be looking at some exam questions. Okay, so again, if we draw a diagram, again, we'll get to what they want, okay? But before that, let's just do what we know, okay? So again, draw a diagram first. So we have P and Q. Now, P has mass 3m, Q has mass 2m. So, there we are. Now, we're told they move in opposite directions towards each other. So that's going to look like P going to Q like this and Q going to P like that, okay? Now the speed of P before is u and Q is 2u, okay? Then we're told after the collision they're moving in opposite directions. Now, usually, pretty much always, you're going to want to take the second particle to go to the right after the collision, okay? So I'm going to call that V2 because if it was to move to the left, it would have to kind of phase through P, right? Especially if P is then moving that way. It would have to phase through P, so that just cannot happen. So it has to move to the right. Generally, an exam tip, you want to take the speed of the second particle to the right forwards, okay? Generally, it's what you want to do, okay? And so, therefore, that leaves, if P moves opposite to that, it's going to have to move that way, okay? To the left, okay? In the opposite direction. So there we are. So that's going to be V1, okay? And so there we are. So let's get cracking. So firstly, we have momentum as usual. So that's going to be 3m lots of u, and then 2m lots of negative 2u, because again, forwards is positive. So negative 2u here. That's going to equal 3m lots of minus v1. Add 2m lots of v2, okay? So hopefully happy with this. And so we can simplify this to get 3mu minus 4mu equals minus 3mv1, add 2mv2, okay? And so there we are. We can divide by m, cancel all the m's. So here we are. So I get 3u take away 4u is minus 3v1, add 2v2. And so hopefully we can see we're going to get minus 3v1, add 2v2 equals minus u. Okay. And so there we are. That's my first equation. Then if I consider restitution, that's going to be E. Again, the standard formula is V2 take away V1 over U1 take away U2. So that's going to be, well, V2 here, take away V1. Now, Again, that's negative, going in the negative direction, so it's minus V1. And then U1 is going to be U, and then U2 is going to be minus 2U, because again, that's negative. Okay, so minus 2U as it's going in the negative, as it's going backwards. So we can simplify this to V2 and V1 over U plus 2U. Okay, and so therefore E will be V2 and V1 over 3U. So we can cross multiply to 3EU is V1 and V2, and there we are. And so then I get these simultaneous equations. So if I rewrite them here, I have minus 3V1 and 2V2, was it? Yes, that's going to equal minus U. Okay, and we also have here V1 and V2 is equal to 3EU. So these are my two equations. Okay, so I want to solve for either V1, V2. Let's triple the second equation. So then we're going to get 3V1 add 3V2 is 9EU. Then if I bring the first equation back, again, you can then see we can add them to get rid of the V1s. So we get 5V2 is 9EU minus U. Okay. Then V2, if I divide by 5, so we get a fifth of 9EU minus U. Then I can factor EU out. Okay. So it'd be U over 5, lots of 9E minus 1. Okay. And there we are. Okay. Let's find V1. Okay, let's just complete it. We're most likely going to need both speeds anyway. Let's just proceed with finding V1. So I'm going to sub V2 into what equation? Okay, let's substitute it into this one, right? V1 and V2 is 3EU. Okay, so then I can obtain V1. So V1 and V2, which is U over 5. Lots of 9E minus 1 is 3EU. Then if I expand this, I get a 9/5 EU minus a 5th U is 3EU. Then I can move everything to one side. So V1 on its own is going to be 3EU minus 9 over 5EU plus a 5th U. And so again, I got common terms EU. I can collect like terms. So 3 lots of EU minus 9/5 lots of EU. It's going to be 6/5 EU, okay, plus a 5th U. And so there we are. Then I can just make this look nicer. I can factor a 5th U out, and then that will be 6E plus 1. Okay, and there we are. Okay, so how does this help with the question at hand? Now, the question, if I get rid of this, the question was asking for the range of possible values of E. Now, that is obviously not just going to say E between 0 and 1. You're not going to get that for 8 marks, okay? We need to sort of tighten this inequality. Okay, we need to be a bit better than just between 0 and 1. So what we're gonna need to do is we're gonna need to look at our speeds. Okay, it's the only thing we can look at here. Now, if we look at the question, we are told after the collision they are indeed moving in opposite directions, and so therefore these directions, they have to be here. So that means these directions must be true. Okay, we're told explicitly that this is what the direction should look like, that they're moving opposite to each other. Okay, obviously if it was the other way around, if they were moving opposite towards each other, that would make no sense. They have to separate, they have to split apart. So these directions must be true. Okay, they have to be moving separate like this. So that means the directions we have taken for V1 and V2 must be true. So V1 must be backwards and V2 must be forwards. Okay, so that means that V2 must be positive, and V1 must also be positive as well. So my answer for V1 must be positive, okay? Because then let's say we get, say, positive 3. Well, that indeed is saying the speed is 3 backwards, but we know it's moving backwards. So that has to be a positive answer for V1 and V2, because the directions must be where we said they are, okay? There's no ambiguity with the directions here. They've told us in the question. So both my answers, V1, V2, must be positive. Hopefully happy with that, okay? Also, there might be some confusion with this. Obviously we're saying V1 is negative. V1's going in the negative direction, but I'm saying that V1, the answer itself, V1, must be positive. I want to stress the difference here. The direction it's going in is negative, which means when we looked at our equations, we negated it. But because we negated it in the equations, the actual answer for V1 must be positive, which tells me it will be indeed moving left, okay? If I had a negative answer like -3 for V1, it would then tell me it's going to the right by 3, but it can't move to the right. It has to be moving to the left. We're told that, okay? So it has to be a positive answer. I want to stress the difference there between the direction of the speed being negative, but the speed itself has to be a positive number, okay? So hopefully that made sense, okay? So with that said, we need to consider the sign of either V1 or V2, okay? We need to consider either of them, okay? So let's say just pick V2, okay? Let's consider V2. Now we've just looked at V2, okay? So I'm going to copy that again. So V2, remember, is U/5 of 9e minus 1, was it? So, as we discussed, V2 must be positive as it's moving forward. As the second particle, was it Q? So, as Q is guaranteed to move forward. Okay, hopefully happy with that. So that means V2 must be greater than 0 because it's moving forward. So we can just sub that in and say U/5 lots of 9e minus 1 is greater than 0. Now, usually again, U is going to be positive. So what we can do is divide by U/5. Again, treat it like an equation, but the inequality will stay where it is. We don't need to worry about negative. We don't need to worry about negative because U is positive, okay? That is because, by the way, U is positive because it's a speed. And remember, speed is always a positive quantity. But usually that's what you're going to want to do with these sort of questions. You can simplify, you can divide by U, and then the inequality stays where it is. It's a positive thing. Hopefully happy with that then. Okay, so we can simplify this sort of inequality to just get this. Then, hopefully you can see we're going to get an inequality for E. So 9e is greater than 1. Therefore, E is greater than a ninth. Okay. And so there we are. So we can then say that E has to be between a ninth and 1. Okay. So there we are. But it might also be wise to consider V1 because we might be able to tighten this inequality even further. Okay. So if we consider now V1, so remember, as I discussed, the answer V1 must be positive as well, because we know for sure it's indeed moving in that direction. So it has to be positive. So if I now consider V1, okay, let's see what happens. So V1 is a fifth lots of 6e plus 1. So V1 is a fifth U of 6e plus 1. Yep. Now, as I discussed, V1 must also be positive. So, again, that's because indeed it's moving backwards. Okay. So it's moving in the so it's moving in the direction we said it is. Okay, so it can't be negative anyway. So that means v1 must be again greater than 0. Well, we know that v1 is this expression here, so let's sub it in. So we get a fifth u of 6e plus 1 greater than 0. Again, we're going to divide by a fifth u to get 6e plus 1 greater than 0. Well, then e is greater than minus of 6, but that doesn't tell me anything. Okay, because I know that's saying that e has to be greater than a negative number. I know that's true anyway, because e is between 0 and 1. E can't be negative anyway. So that doesn't tell me anything, unfortunately. So overall, my final answer, my final inequality for e is this 9th to 1. Okay. And there we are. Okay. Hopefully happy with that. Okay. Then for part B, it says, given that Q loses 75% of its kinetic energy, find the value of E. So now it's referring to loss of energy, but it's specifically referring to Q here. So it's not the total loss in energy, it's just the loss of energy of Q. And more specifically, we're told it loses 75% of energy. So what we can say about that is that the final, so if it loses 75% of energy, it has 25% of energy remaining. So that means the final kinetic energy has to be 25% of the original energy before, right? So 25% of the before kinetic energy. Okay, hopefully happy with that. So if it loses 75%, it's 25% remaining. Okay. And so we can alternatively say that 25% of something is going to be 0.25 times it, right? And so we can use this sort of equation here. Okay, hopefully happy with that, and hopefully happy convert the percentage to a decimal like this. Okay, so there we are. So we're going to use this here. Okay, I'm going to do it up here. So, okay, so that's saying that the final kinetic energy of Q, remember, is 0.25 lots of the initial energy of Q, okay? So actually what I'm going to do is work out these two parts. So I can work out the final and before kinetic energy separately first. So the final kinetic energy, okay, well, the final speed is v2 and the mass of Q is 2m. So it's going to be half times 2m times v2 squared, right? And so that will now that will simplify to m lots of v2 squared. But we know what v2 is, right? We worked out that v2 is u over 5 of 9e minus 1, right? So that's going to be u over m lots of u over 5 of 9e minus 1 all squared. Hopefully happy with that substitution there. So we can expand this to get m lots of, now u over 5 squared is going to be u squared over 25, and then 9e minus 1 all squared. Okay, then we can simplify this to 1 over 25 lots of mu squared of 9e minus 1 squared, and that is my expression there. Then we can calculate the before energy. So that's going to be half times the mass of 2m, and the initial speed was 2u, okay? So it's going to be 2u squared. And we can simplify that quite nicely, so that's going to be m lots of 4u squared. So that's going to be 4mu squared, and there we are. Okay, so now I've got my expressions for the before and after kinetic energy, so I can now effectively substitute into this sort of equation we got here, right? So therefore the final kinetic energy, which was this 1 over 25 mu squared lots of 9e minus 1 squared, so 1 over 25 mu squared of 9e minus 1 squared, that's going to be 0.25 lots of the before kinetic energy. So 0.5 times this for mu squared, right? So 0.25 times 4 mu squared. Then we can simplify, so that'd be 1 over 25 mu squared of 9e minus 1 squared. That's going to just be 1 lots of mu squared. Okay, hopefully happy with this. We can actually then divide by the mu squareds and cancel them out. So now we just got 1 over 25 of 9e minus 1 squared is 1. And that's a lot nicer to solve, right? So hopefully it's a lot more apparent now how we can solve. So what we can then do to get rid of the fraction to make it even nicer, let's times by 25. So 9e minus 1 squared is just 25 here. Now, you might just think then expand the bracket, solve the quadratic. That's absolutely fine, but actually we can effectively just root it now, because if we square root it, we can then say that just 9e minus 1 is plus or minus the root of 25, and then we can solve from here. Okay, but you can solve however you like, but here we are. And actually that simplifies to plus or minus 5, right? Root 25 is 5. Then I can add 1 to both sides, so 9e is just 1 plus or minus 5. And therefore, E is just going to be a ninth of this, okay? And there we are. And so then, my two solutions from this, well, if I do the positive case first, E is going to be a ninth of 1 plus 5. That's going to be 6 over 9, which simplifies to 2/3. Or, the other case, when it's negative, it's going to be a ninth of 1 minus 5. That's going to be minus 4 over 9. So these are my two possible solutions here. So again, you can solve this however you like, but you should get these two solutions here. Now, of course, we can't have a negative value for E because E is positive. Again, that's because E is between 0 and 1. Again, you must remember that. And so, E can only be a third. And 2/3, and so that is my solution for E there. Okay, so now we're going to look at this question here. Now we can also apply kinetic energy to things bouncing up and down from the floor, which we looked at last time, right? So if we looked at the last part, the last section, we looked at things bouncing up and down from the ground. You'll see questions like this. So the idea is it's in the air and then it will fall down to the ground, right? And so initially it's released from rest, okay? So it starts with 0 speed, and then it's going to hit the ground with a speed, say v, okay? So there we are. I am also told it dropped 3.6 meters downwards. So this whole height is 3.6, okay? And I also know the acceleration downwards, okay? When it's falling, it's 9.8, okay? It's G, okay? So hopefully happy with that. So, if I now use Suvat, so I know S, my distance here is 3.6, U, the initial speed is 0, V is V, and A is 9.8. I don't need T here, so the Suvat equation, so I can solve for V here, so the Suvat equation that ignores T is V squared is U squared with 2AS, right? So I can apply that formula here. So that means V squared is going to be 0 squared at 2 lots of 9.8, lots of 3.6. So V squared, if I simplify this, that's going to be 70.56, okay? Then I can root that to say it's going to be 8.4, okay? Quite nicely, 8.4. Okay, that is my full answer for V here. So that shouldn't be unfamiliar. Hopefully you remember that from last time. So there we are. So this speed here is 8.4, and then of course once it bounces down, it's going to then bounce back up off the ground. So now we've got this scenario here where the ball is bouncing upwards, okay, and it leaves the ground with speed u, okay. U, I'm going to call it u dash, okay, to represent the new initial speed. Okay, now that's what it wants me to work out. It wants me to find the speed u dash after it hits the ground, so when it jumps, when it bounces off the ground, okay, that's this speed here. So okay, so what can I do here? Well, you might be thinking then, well, I can consider the restitution, right? Because when it hits the ground. So I know the ball hits the ground. It hits the ground with this speed 8.4 we worked out, and then it bounces up afterwards with this speed u. Okay, u dash. But the issue is I don't know e. I do not know e. Okay. But I don't need E, because it's actually told me, quite interestingly, it's told me information about the impulse instead. Now, what you need to know is impulse acts always perpendicular to the surface. So if I extend the line like this, the impulse, again, that's the force, that's sort of the impact as a result of the collision, that acts perpendicular to the ground or the surface, okay. So the impulse acts that way. Now, we also know that impulse is mv take away mu. So if we substitute the impulse here, which is 4.2, then we can say that 4.2 is going to equal m. Now m, the mass we're told is 0.3, okay. So the mass is going to be relevant here. So 0.3 lots of the final speed, which is u dash, over the 0.3 lots of the initial speed. Now that's 8.4, but once again, direction matters. We are taking upwards as positive here, if you will, okay. So that's going negative direction, so it's going to be minus 8.4, okay. And so we can simplify this to 4.2 is 0.3 lots of u dash plus 2.52, okay. And so therefore 0.3 lots of u dash is going to be 4.2 take away 2.52, so that's going to be 1.68. Therefore u dash is going to be 5.6, okay, and there we are. Now that answer also does, you can tell it makes sense with the sign, because indeed we know that that speed u dash has to be going up, it has to be positive, okay. So indeed the positive sign of the answer makes sense here, okay. So that tells me indeed the speed afterwards is going up, as we expect, because the ball will bounce upwards, right. So there we are. Anyway, that's that question done. Okay, and then in part B, we're told to find the kinetic energy lost. So, okay, so the loss in kinetic energy as it bounces off the ground. So the loss in kinetic energy, that's going to be the kinetic energy before, take away the kinetic energy after, as usual. Now, we can use this diagram here. So quite conveniently, we've got all our speeds before and after here. We also know that, again, the mass was 0.3. So the kinetic energy before, well, the speed is 8.4, the mass is 0.3. So it's going to be half times 0.3 times 8.4 squared. And then afterwards it's half times 0.3, and the speed afterwards was this 5.6, right? And that'd be squared, right? Again, you can see that after. You can see it here, right? So this is my speed before, 8.4, then the speed after, 5.6, okay? Hopefully you're happy with that. Then I literally could just put this in the calculator, and then we're done. and that's 5.88, and that'd be joules, right? So that's my loss in energy there. And there we are. So again, you can also consider kinetic energy loss and with collisions with grounds and the walls as well. Okay, not just between two balls, but also between a floor or a ground or something like that, right? So there we are. So hopefully that's helped, but I'll see you next time.